Good day, everyone. I am pleased to introduce our paper, Transferable Multimodal Attack on Vision Language Pre-training Models. Adversarial attacks involve making imperceptible modifications to the original input data to deceive machine learning models, leading to incorrect predictions or classifications by the model. This type of attack reveals vulnerabilities even in state-of-the-art deep learning models for tasks such as image classification or text classification. Transferable attacks refer to the transferability of adversarial examples between different models, meaning an adversarial example generated for a specific model or surrogate model can deceive not only that model, but also other well-trained black box models, even if their structures or training data are different. Our work focuses on the transferability of adversarial examples against vision language pre-training models. Vision language pre-training models are designed to learn joint representations of vision and language by processing both images and natural language text. These models typically involve the intersection of computer vision and NLP fields, enabling tasks such as vision language retrieval, visual entailment, visual grounding, visual question answering, and more. We found that existing adversarial attack strategies against vision language pre-training models exhibit very weak transferability. Additionally, directly applying existing adversarial attack methods for single-modal models results in significant performance degradation on vision language pre-training models. This inspired us to design more powerful and transferable adversarial examples. As shown in the diagram, compared to baselines, our proposed TMM demonstrates better cross-model transferability. Now, I will provide an overview of the contributions of our paper. Firstly, our work is the first to examine transferable adversarial examples on vision language pre-training models, focusing on modality consistency and modality discrepancy features. Second, we propose the TMM framework for generating transferable adversarial examples for VLP models, which compose attention-directed feature perturbation and orthogonal guided feature heterogenization. Third, TMM significantly enhances the attack success rate by an average of 47% compared to the existing methods, while also maintaining good stealth. Last, additional explorations demonstrate transferable attacking ability of TMM against powerful large generative vision language models in black box settings. Here, let's first introduce the threat model of our work. Firstly, the attacker can obtain partial clean samples and can access publicly available white box VLP models, but the attacker cannot know their target model, including the structure, type, and parameters of the target model, placing it in a completely black box state, which is a perfect simulation of real-world scenarios. Secondly, the attacker can only generate adversarial examples based on a specific white box VLP model and then attack a target VLP model, without being able to perform any additional operations such as fine-tuning or querying. Lastly, the attacker aims to achieve a high success rate in causing downstream tasks of VLP models to produce incorrect results. Now, I will provide an overview of the framework we propose. TMM consists of two parts. Firstly, the attention-directed feature perturbation (ADFP) strategy. Given the widespread use of cross-attention in many VLP models to facilitate cross-modal interactions, we believe this shared module can leverage modality consistency features to enhance transferable attacks. By identifying modality consistency feature regions between different modalities under the guidance of cross-attention, and replacing relevant text with more perturbation budget allocated to critical regions within the image, the attacking ability can effectively transfer across multiple models. Secondly, the orthogonal guided feature heterogenization (OGFH) method. Considering that VLP models rely more on the aligned features between different modalities in the decision-making process, our goal is to heterogenize additional embedding features into discrepant features to enhance the attacking ability. By orthogonalizing the modality-fused representation, we guide the adversarial perturbation to incorporate more modality discrepancy features within the encoded embeddings, thereby promoting stronger attacks. Specifically, to enhance transferability, we propose the Attention-Directed Feature Perturbation strategy. ADFP primarily perturbs modality consistency features, which represent decision-relevant features shared between different VLP models. For example, both text and visual inputs may share attributes such as color or shape information, which are highly relevant to executing transferable attacks. Specifically, ADFB first identifies modality consistency feature regions between different modalities through the attention mechanism as shown in the bottom left formula. It then guides the perturbation training of image modality consistency feature regions through structural similarity loss and replaces related texts with the bottom right lieutenant loss. This loss guides the replacement of target texts with text perturbations that can significantly impact the VLP representations. To enhance the attacking ability, we designed an orthogonal guided feature heterogenization method. OGFH mainly focuses on perturbing modality discrepancy features, which represent each modality's unique features that the VLP model's decision does not rely on. For example, in text input, a unique attribute could be grammar, while in visual input, it could be pixel intensity. Since these attributes do not contribute to the decision-making process, enhancing these unique, specific attributes introduces ambiguity into the model's decision-making process. Considering that existing VLP models often intentionally use different training strategies to ignore modality discrepancy features that exhibit negative impacts on models. Motivated by this observation, we exploit the idea of orthogonalization to enrich discrepant features to perform attacks. Specifically, we designed a cosine orthogonalization optimization strategy through these three losses to guide adversarial perturbations, heterogenizing more embedded features into discrepant ones, thereby enhancing the attack capability. Here we present the results of our proposed TMM, where adversarial examples generated on the ALBEF model are more effectively transferable to other black box VLP models compared to baselines, with an average increase in attack success rate of 47%. Due to time constraints, please refer to our paper for a detailed analysis of the experimental results. We further tested the effectiveness of our proposed TMM on large generative vision language models. We used a language template. Does the picture depict? Only answer yes or no. To assemble adversarial text and combine it with adversarial image inputs, asking the large generative vision language model to make a judgment on the question. The table shows the number of samples for which the model gave incorrect results, with red numbers indicating percentages. Our proposed TMM achieved a higher attack success rate compared to baselines. Regarding defense mechanisms, traditional adversarial defense methods focusing on visual or text modalities may not be suitable for VLP tasks due to the need for class labels and output probabilities. We explored input space defenses but found existing methods ineffective against TMM attacks. Adversarial training has shown promise as an effective defense strategy, particularly in self-supervised learning for VLP tasks. While we could not conduct adversarial training due to resource constraints, we believe it could significantly enhance model robustness against TMM attacks. In conclusion, our work introduces the Transferable Multimodal Attack framework for generating transferable adversarial examples against VLP models. We propose novel strategies to enhance attack transferability and effectiveness, leading to improved attack success rates across various downstream tasks. Our experiments highlight the potential adversarial risks associated with LVLMs and emphasize the need for robust VLP models. For future work, we aim to explore advanced training strategies and model architectures to build more reliable VLP models robust to adversarial attacks. That's all. Thank you everyone for listening.